number can either be an integer or a float. Numbers without fractional components are integers, while numbers with fractional components are called floats, which is short for floating point number. Integers in Rust may either be signed or unsigned. Signed integers are integers that carry a sign. They can be negative, positive, or zero. Unsigned integers, on the other hand, are integers without a sign and are either positive or zero. Signed integers are labeled with an I, followed by the size of the integer specified in bits. Unsigned integers are labeled with a U, followed by the size of the integer. We can specify the size and type of the integer by adding the label at the end of the number literal. If we don't specify the type of integer, the variable is given a signed 32-bit integer by default. There are 12 variants of the integer type in Rust, and they are classified by sign and size. Then there are the iSize and the uSize variants. Their size depends on the architecture of the computer on which the program is running. For 32-bit systems, the iSize becomes I32 and the uSize becomes U32. Likewise, for 64-bit systems, the iSize is I64 and U64 for uSize. They are mostly used in indexing a collection like arrays and vectors. Each integer variant can store integers of a certain range due to their size and sign. For a signed integer in, the range is between -2 to the power of n-1 to 2 to the power of n-1 minus 1. For an unsigned integer un, its range is between 0 to 2 to the power of n-1. So i8 can store integers from -2 to the power of 7 to 2 to the power of 7 minus 1, which is -128 to 127. While U8 can store integers from 0 to 2 to the power of 8 minus 1, which is equal to 255. We can do this for other integer variants to get their ranges. 8 bits equals 1 byte, so an i8 and u8 integer takes up 1 byte in the memory. 16-bit integers take up 2 bytes, 32-bit integers take up 4, and so on. To get the size of a data type, you can use the sizeOf function obtained from the main module of the standard library. There are several ways of writing a number literal. For large numbers, we can separate the numerals with an underscore for better readability. We can also write integers in hexadecimal format, in octal or in binary form. For hexadecimal formats, we prefix the integer with 0x, 0O for octal, and 0b for binary. When we print out the value of these integers, it will be displayed in isdecimal formats. To display an integer in hexadecimal form, in the curly brackets, we specify we want the integer to be formatted to hexadecimal by including a colon followed by an x. For octal, we use 0 instead of x, and for binary we use b. One more thing we are going to talk about before moving to a floating point number is an integer overflow. Since each integer variant can only store integers of a specific range, what happens when it overflows? Here we have a U8 integer whose value is 255. Since 255 is the largest U8 integer, if we add 1, it overflows. When we run this program, our program won't compile since the compiler can't detect the overflow. If the variable comes from an external source like the command line, the compiler can't detect an overflow if we perform arithmetic operations on it. Here we have a program that reads 2 inputs from the command line and passes them to a U8 integer, then prints the sum of those 2 integers. If we run this program in debug mode and enter 2 integers whose sum is greater than 255, the program panics. But if we build and run this program in release mode, for the first integer we enter 255 and for the second we enter 1. Our output is 0. This is because in release mode, instead of panicking, our program wraps it from the minimum. 256 becomes 0, 257 becomes 1, and so on. To handle the cases of overflow explicitly, you can use the wrapping add method, which wraps it from the minimum. The overflowing add method wraps the sum but returns a tuple where the first element is the wrapped sum and the second element is a boolean indicating whether the sum was wrapped. The checked add method returns the null value if it overflows, and the saturating add method saturates the value at the maximum or minimum depending on where it overflowed. Floating point numbers are numbers without fractional components or decimal points. In Rust, a float can either be 32 bits or 64 bits in size. 64-bit floats have higher range and precision than 32-bit floats. Floating point types are specified with an F followed by the number of bits. We can specify the type of float after the variable name and a colon, or at the end of the number literal. If we do not specify the type of float, it is given an F64 by default. A 32-bit float is a bit faster and uses less memory than a 64-bit float, but it comes with less range and precision. The minimum and maximum values a 32-bit float can have is this, while that of a 64-bit float is this. 32-bit floats are best used in graphics and video processing, where memory usage is a primary concern and their range and precision are significant for the task. 64-bit floats, on the other hand, are used in scientific calculations and statistical analysis where precision is very necessary. There is also a kind of number literal called byte, which stores ASCII character literals as an 8-bit unsigned integer. If we print out the variable a, we get the numerical value of the ASCII character a. Replacing the character literal with a string literal will result in an array of bytes. Printing out this variable, we can see it's an array containing the numerical value of each ASCII character. Thanks for watching.